Hello everyone, I'm Sojin Lee from Korea University. The title of my paper is Diffusion Prior-Based Amortized Variational Inference for Noisy Inverse Problems. In an inverse problem, we start with the Ford model y equals hx0, where a clean signal becomes degraded. Restoring the original signal is challenging because there are multiple possible solutions, known as a many-to-one mapping problem. Let's align the Ford model equation for the noisy inverse problem with the figure. Clean image x0, degradation matrix H, degraded image hx0, additive Gaussian noise n, measurement y. For evaluation, we compare the restored image x0 hat to the ground truth x0. Let's compare our proposed method DABI with previous methods. This video compares DABI with LEDDIF. While LEDDIF generates one image, DABI generates 1,000 images. In other words, DABI shows 1,000 times faster inference speed. The inference speed is shown in a log scale graph. DABI requires 20 to 1,000 times fewer steps than the baselines, due to its one-step sampling, making it extremely fast. In fact, DABI generates an image in just 0.04 seconds, which is approximately 1,000 times faster than LEDDIF. DABI not only offers fast speed but also generates high-quality images that are closest to the ground truth image. DABI and previous methods are compared from two perspectives, inference and optimization. Existing methods use iterative sampling along the reverse diffusion process that rely on a pre-trained diffusion model. However, DABI performs single-step sampling using a parameterized implicit distribution. Additionally, previous methods require measurement-wise optimization. It means that they need test time optimization for each sample. In contrast, DABI trained the neural network through amortized optimization. As a result, DABI requires no additional optimization at test time. We introduced DABI, which performs amortized variational inference using an implicit distribution. To solve the inverse problem, we need to find the true posterior px0 given y. Our goal is to optimize an implicit distribution that approximates this true posterior using variational optimization. We achieve this by minimizing the KL divergence between the implicit distribution parameterized by our neural network and the true posterior distribution. When expanding the KL divergence and excluding the constant term, we are left with two terms. The data consistency term ensures that our generated sample aligns with the given measurement y. Using the equation of the Ford model, we can calculate it analytically. The last term is the KL divergence between the implicit posterior and the clean image distribution. We approximate the clean image prior using a pre-trained diffusion model as a prior. Now we want to optimize the implicit distribution to align with the clean image distribution. However, we face the disjoint support problem. When two distributions do not overlap, the KL divergence becomes infinite. To alleviate the disjoint support problem, we use the diffusion forward process by smoothing the distributions. Let's minimize the discrepancy between two distributions and an arbitrary time step t1. To estimate the score of an implicit distribution at any time step, we introduce an implicit score function as psi. Next, we update the neural network to minimize the discrepancy between the implicit score function and the diffusion prior. When the implicit distribution is updated, the implicit score function must also be updated. Therefore, we alternate the optimization of both networks. We introduce an implicit score function to compute the score at each time step for the implicit posterior sample, training it using the denoising score matching loss. Furthermore, to improve the robustness of implicit neural network to diverse noise measurement y, we introduce the perturbed posterior bridge, or PPB for short. We adjust hyperparameter A along with the diffusion schedule beta t from DDPM to obtain an intermediately set of trajectories between the y and x. Moreover, we introduce a perturbation schedule for noise measurement. We then input the intermediate point YA into the neural network to estimate the clean image. This approach allows us to optimize the implicit distribution with more diverse samples drawn from PPB between Y and X. We observed it effectively enhanced the generalization to unseen measurements even out of distribution. For the out-of-distribution experiment, we set a test dataset different from the training dataset. These examples confirm Davi's strong ability to generalize to unseen distributions. Furthermore, we demonstrate Davi's versatility through 5 restoration tasks. In summary, Davi efficiently performs one-step posterior sampling without the need for optimization at test time. Thank you for watching my presentation video.